Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, we're back again for the fourth lecture in week 1 of the course called Fundamentals of Atomic Force Microscopy. This is part 1 of a two-part course. And in this particular lecture, we are going to talk about the intermolecular forces, in particular due to a ion-dipole interaction. And by way of summary, it's kind of useful to provide this overview in which we're going to actually talk about how an individual ion interacts with other ions or other molecules that may or may not have a dipole moment. And the critical question in this discussion always is keeping track of the interaction energy that characterizes these various entities, and in particular how this interaction energy depends on separation. So that's always the question of interest. We've already discussed in the previous lecture the interaction of an ion with an ion. That's very simple. That's mostly just a reminder. We've also discussed how an ion interacts with a polar molecule that's held at a fixed angle. In this lecture, we're going to talk about what happens if the polar molecule, if the dipole moment of the polar molecule is free to rotate. So we're going to do an angle average calculation, and we're also going to extend the discussion to nonpolar molecules and discuss this idea of polarization and induced dipole moments. So let me remind you what we've already discussed. If we have a point charge plus Q located at some point in space, we have another molecule that's represented by this dipole, and this dipole is located at a distance z from the point charge. The interaction potential energy between this point charge and this dipole is written on the, given by the equation on the right of the slide. It depends clearly on the angle theta. It depends on how the dipole is oriented with respect to the point charge. In real situations, it's possible that this dipole can fluctuate, and so all possible angles of theta must be taken into account. And the question is, how do you properly average over theta in a situation where the dipole moment is in thermal equilibrium with some thermal bath at some temperature T? And of course the answer to that question is we have to use Boltzmann statistics. So we have to rely on what we've learned from some of our introductory courses in thermodynamics. So for those of you that maybe have not had a recent course in thermodynamics, it's probably worthwhile to have a very quick review of how you might calculate a thermodynamic average of, let's say, some quantity Y in a system that is in thermodynamic equilibrium with a reservoir at temperature T. Now this quantity Y can be almost anything. It could be the magnetic moments, it could be the electrostatic polarization, it could be any number of a wide variety of quantities. In this case, we're just trying to lay out the basic ideas on how you might calculate the thermal average of this quantity Y. And the way this calculation proceeds is you have to have some knowledge about the physical quantities Y that you can measure. So you maybe make a simple table where you list all possible values of Y that might be measured. You have to relate those possible measurements to the energy of the system when you make that measurement. So each quantity Y is associated with some energy E. And then it's also possible that each state of the system is characterized by some multiplicity, some weight, which we call W. And this weighting factor could be unity in a real simple case for every possible value of Y, or this weighting factor W could depend on, could vary in some complicated way depending on the nature of the system. So if you want to calculate the thermal value of Y, what you have to do is you have to find the probability that each value of y, what the probability is that each value of y would be observed. And then the thermal average of y, which is represented by this angle bracket notation, right? This thermal average is then represented by the sum of all possible values of y times the probability that each possible value of y occurs. That's p sub r, right? And the thermodynamics comes in calculating this parameter p sub r. That's where the thermodynamics of the problem arises. So the probability of finding a state with energy E in a system that's in thermal equilibrium, that's given by multiplying the multiplicity or weight of each state. So if we call each state, if we label each state with an index R, right, the probability of finding state R requires us to know the weight of that state, W sub R, and the energy of that particular state, E sub R. And if we multiply the weighting factor times this Boltzmann factor, e to the minus E sub R over KT, that forms the numerator for the particular state R. The denominator is just the sum of the weighting factor times the Boltzmann factor for all possible states of the system. So that includes a sum over R. So the most probable value of some quantity y with possible values y sub r is then given by the last equation in this slide. It's just a sum of all possible values y multiplied by the probability that each state y, that each value is observed. This is a standard formula that's used to calculate thermodynamic averages, and hopefully this brief review will remind you of what you've already learned in maybe an introductory thermodynamics course. Now in our case, we're interested in averaging over all possible angles of this dipole, of this orientation of this dipole moment. Right, so in our case, we have to calculate the energy of interaction between a point charge and a dipole moment, angle averaged over all values of theta. So that's the challenge that we're going to face. And in our case, since theta is a continuous variable, we no longer have sums. We have to replace the sums by integrals because we're going to integrate over all possible values of theta. So the details of this calculation are worked out in the appendix for those of you that are particularly interested. And what we're trying to do is we're trying to calculate the thermal angle average to this interaction potential energy U, and we're doing that at a fixed distance Z between the ion and the dipole moment. We're going to integrate the interaction potential energy. This interaction potential energy is equivalent to Y in the previous slide. We're going to integrate that over all possible values of theta. And the weighting factor for this calculation is just this factor sine theta that appears in red in the top equation here. When you do this calculation, it becomes useful to make two approximations. One approximation is you assume that the interaction potential energy is small compared to KT. That then allows you to expand the Boltzmann factor, this exponential factor that appears in this thermal averaged equation. That allows you to approximate it by a Taylor series expansion, and you can then just keep the first term in that Taylor series expansion. So if you follow through all that arithmetic, for those of you that are interested, please refer to the appendix. But when you follow all that through in a logical way, you'll end up with the last equation that's presented here. And there's a couple of features in this equation that are important to note. First of all, the thermal average of U, when all possible angles theta are taken into account, that interaction potential energy is negative. That means that there will be a net attractive interaction between the ion and the dipole moment, even when the dipole moment is allowed to have all possible orientations. The second feature to note is that the thermal energy, KT, now shows up explicitly in the formula for the thermal averaged U of Z. This is a clue that we've done in angle averaging in this particular case. And the third thing to note is that this interaction potential energy now varies as 1 over the separation to the 4th power. Right, so we've gone from a 1 over Z squared interaction potential energy for a dipole at a fixed orientation. When we average over all orientations, we go from 1 over Z squared to 1 over Z to the 4th. So that's another important feature of this result. Just to try and reinforce this conclusion, I prepared this slide which summarizes the two results. In the left part of the slide, we've got fixed angle interaction potential energy. In the right-hand part of the slide, the upper part, on the right, we show the answer for the interaction potential energy when the dipole is angle averaged over all possible values of theta. And then I just provide a plot. In this particular case, I take a dipole of 1 Debye. I take a point charge of +1 electron. This is 300 degrees Kelvin. And the ion and the dipole are embedded in the dielectric medium with dielectric constant 2.5. And I just compare the interaction potential energies for a few fixed angles of 30 degrees, 75, 105, and 150 degrees, right? I compare those to the angle average case, which is indicated by the red curve here on this slide. And what you can see is that for fixed angles, the interaction potential energy extends over a rather large distance, right? Over 2 to 3 nanometers. The details depend on the actual angle that you choose, but there's a non-zero value for the interaction potential energy when the ion and the dipole are separated by 2 or 3 nanometers. When you do this angle average case, when the dipole moment is free to rotate as it moves around with respect to the ion, now you have to get much closer, and that's indicated by the red arrow in the bottom part of this graph, right? You have to get on the order of a nanometer or so before the interaction potential energy starts to deviate significantly from 0. So the angle average case gives you a much shorter range interaction than the fixed angled calculation. So that's the main conclusion to note from this discussion. The next topic is what happens if a molecule or an atom does not have a permanent dipole moment, right? How does it interact with, let's say, an external electric field? Just thinking about the problem first glance, you might say, well, there would be no interaction between this nonpolar molecule and, let's say, an electric field that happens to exist in space. But that's not the case, because what happens is the external electric field induces a dipole moment in this atom or molecule. And this induced dipole moment depends on the strength of the electric field, E, right? And the proportionality constant between the induced dipole moment and the applied electric field is a parameter called alpha 0. That's referred to as the electronic polarizability of the atom or molecule in question. So at this point, we don't really care how the electric field is produced. The electric field could be produced by an ion. It could be produced by a nearby dipole, by a nearby molecule which has a permanent dipole moment. At this point, we don't really care. All we care is that there's an external electric field that induces a dipole moment in an atom or molecule, which is a nonpolar atom or molecule. So this electronic polarizability is a number that can be measured experimentally. It has units of Coulomb squared meters per Newton, and it's often written in this simplified form that alpha 0 is equal to 4 pi epsilon naught. Epsilon naught is the permittivity of free space times another parameter alpha, which is referred to often in the literature as the electronic polarizability volume. And I think the case I'm trying to make here is that this electronic polarizability volume is roughly proportional to the volume of the atom or molecule that the dipole moment is induced in. So if the atom or molecule has a diameter, let's say 2 capital R, as indicated in the right-hand cartoon up here, then the electronic polarizability volume is on the order of R cubed. That's the volume of that particular atom or molecule. And to a reasonably good approximation, polarizabilities scale with volumes or sizes of atoms or molecules. And I just work through some numbers on the bottom here to illustrate that point. You can look up what the polarizability volume is for a water molecule. You can take the cube of that, and you would then infer that the radius of a water molecule is on the order of 0.114 nanometers. If you then look up what the actual radius of the water molecule is, the accepted value seems to be a number on the order of 0.135 nanometers. So to a reasonable approximation, you know, the cube of the polarizability volume is roughly comparable to the accepted size of a water molecule. And it just tries to make the case that this polarizability scales with the size of atoms and molecules. So the bigger the atom, the bigger the molecule, the bigger the polarizability tends to be. So the fact that nonpolar molecules can be polarized by external electric fields is an important result, right? Because it just generalizes this whole discussion in a very interesting way. And I indicate that in this particular diagram where we have a point charge, an ion plus capital Q, interacting with a nonpolar molecule. And I indicate schematically the electron charge cloud of this nonpolar molecule. And to a first approximation, that electronic charge cloud has to be reasonably spherically symmetric because the molecule does not have a dipole moment. But when that molecule, that nonpolar molecule, interacts with this point charge, right, the electronic wave functions of the molecule can shift subtly, and I've tried to indicate that in the bottom diagram, right? The shift is going to be determined by the direction of the electric field that acts on this nonpolar molecule. Well, when we have a point charge plus Q, when we have an ion, the electric field from an ion is radially outward, right? So that dictates the orientation of this subtle rearrangement of the electronic wave functions. And I've tried to indicate that schematically here by this orange-colored ellipse, which is oriented with its charges in such a way to interact with the lowest possible energy with the electric field produced by the ion capital Q. The dipole moment that's going to be induced in that nonpolar molecule is then the polarizability of that molecule, alpha 0, times the electric field E that's produced at the point of the molecule by the ion, right? The ion, which in this case is labeled capital Q. And so the other point I'll make is that the orientation of this rearrangement of the electronic wave functions, that orientation is always dictated by the direction of the electric field produced by the ion. And that implies that this angle theta is always equal to pi. And so these expressions for the induced polarization that I give on the bottom here, right, those expressions always have to be evaluated for the appropriate angle. And in this case, it's pi, right? So this gives us an equation that allows us to calculate what the interaction potential energy is due to this induced dipole moment, right? So you can see now P is labeled P induced to try to convey to you that the induced dipole is going to be related to the polarizability alpha naught and the electric field E that the nonpolar molecule feels. So in this set of equations, I just work out the equations in detail, and I end up with an expression which, not surprisingly, includes the polarizability of the nonpolar molecule. That's a number that you're going to have to look up. And it also demonstrates that this interaction potential energy varies as 1 over z to the 4th, right? So again, this is a rather short range interaction. It compared to, let's say, an ion interacting with a dipole moment that's permanent in a nearby molecule. In this case, this particular slide, I just wanted to put some numbers in just to give you a sense of how big these interaction potential energies could be. So I take the case of a lithium ion inducing a dipole moment in an ethanol molecule, just as an example. So I have the relevant parameters for ethanol listed in the top table here. Note that ethanol has a permanent dipole moment of 1.7 dBi, but in addition to that permanent dipole moment, this nearby lithium ion could also induce a dipole moment in the lithium or in the ethanol molecule. And in this particular case, we're calculating the interaction potential energy due to this induced dipole moment. Okay, and so you can track through the numbers. It's the equations are written out clearly for those of you that may not have familiarity with the set of units that we're using, right? But at the end of the day, you find out that the interaction potential energy due to this induced dipole moment in the ethanol molecule is about 8 × 10⁻⁷ electron volts. It's negative, which means there's an attractive interaction that occurs. And this is a reasonably small interaction potential energy, right? Especially compared to thermal energies, kT, which are on the order of 0.026 electron volts, 26 millielectron volts. So thermal energies would dominate interaction, would dominate the interaction between ethanol molecule and this lithium ion, at least for this separation of 2 nanometers, okay? As the ethanol molecule gets closer to the lithium ion, the interaction potential energy, of course, goes up as 1 over z to the 4th. So, but for 2 nanometers, the interaction would be negligible compared to thermal energies. In the next slide, I just compare this interaction of the lithium ion to the angle averaged dipole moment of the ethanol molecule. So in this case, I have to use the interaction potential energy that we obtained from the angle average calculation. If you go back, that's slide 6 of this particular lecture. So I calculate the interaction potential energy due to the angle average permanent dipole moment, and I compare it in the last equation on this slide. I compare it to the interaction potential energy of the induced dipole moment. And what you can see is that the interaction due to the permanent dipole moment is about 4.6 times as large as that produced by the induced interaction. And this is, of course, all for 2 nanometer separation. The ratio of these two numbers clearly is going to depend on the well, actually, it won't depend because both interactions vary as 1 over z to the 4th. So the particular z values will cancel out here. So for all separations z, the thermally averaged permanent dipole moment wins out over the induced dipole moment. So by about a factor of 5. So up next, we'd like to extend this discussion in an important way. Because when we do atomic force microscope experiments, we usually don't have ions free floating around. Usually we have a tip that's electrically neutral interacting with a substrate that's electrically neutral. And so the situation related to ions is not so relevant. And in particular, we're going to have to discuss what happens when two molecules or two atoms start to interact one with another with these, by way of these dipole interactions. So that's the next topic that we'll cover in this set of week 1 lectures.